All right, everybody. So this is Unit 3 review. So this unit focused on magnetism and alternating current circuits. So how we create electricity and how those circuits work for different elements. So the conceptual part I'm going to skip over because you can read through that and kind of look through your notes and find those answers. But the problems I'm going to take some time and go through, and there are some conceptual elements in these problems anyway, so that'll be good. So the first one reads, magnetic field of 16 Tesla acts in a direction going due west. An electron is traveling due south at 8.1 times 10 to the fifth meters per second, and it wants to know what are the magnitude and direction of the force acting on the electron. So underneath the box, I've worked it out, and these unit review answers are online. Kind of just looking at the problem, I drew a picture of what's going on. So the south is down and the magnetic field is going west, so that would be to the left. And so they're perpendicular to each other. So if you think about it that way, that's fine. And I just labeled the different factors. So the magnetic field strength is 16 Tesla, so that's B. The charge is an electron. So an electron has a charge value of 1.6 times 10 to the negative 19th coulombs. And then it's a negative charge. And then the speed of the electron is 8.1 times 10 to the fifth meters per second going south. So we're going to use the FB equation for the force acting on a charge. So it's QVB sine theta. Because west is left and south is down, then they are 90 degrees to each other. So that's where I got 90 from. So I just basically multiply the three values that are given, and I got 2.08 times 10 to the negative 12th newtons. So that's the amount of force. Looking at the direction, we're going to use the right-hand rule. So with the right-hand rule, you put your thumb in the direction of the velocity, so that'd be pointing down towards the bottom of the page. Your fingers line up with the magnetic field, so that's going to the left. And your palm pushes in the direction of the force. So the right-hand rule is set up for a positive charge. So if it was a positive charge, we'd be pushing into the page, but it's a negative charge. So Q is negative, so it goes the exact opposite way, and it would be out of the page. So let me get rid of that. There we go. So the answer here is that the magnetic force is coming out of the page. All right. So for, for number 2, more of the right-hand rule idea. So same idea. So thumb in the direction of the velocity, fingers pointing in the direction of the magnetic field, and your palm pushes on the charge in the direction that your palm faces. So these are all positive, so it's a little bit easier. So you don't have to flip anything. So we're going to put our thumb going to the right because this arrow represents the velocity of the charge. And our fingers are coming out of the page or towards us. So the magnetic field is coming out of the page. So if you look at your hand in that orientation, your palm is pointing down. So for the first one, for A, it's down. B, these crosses are supposed to represent X's, so your fingers are going to point in, your thumb is going to the right, and your palm's going to push up, so that's why that one's up. And then we're kind of doing the reverse, so our thumb is going left, but our fingers are coming out, so I have to orient my hand so my palm is facing up, and then the last one is facing down. If it was a negative charge, these would be reversed again. So just like in the last problem, if it was a negative charge, it would be the exact opposite here. So A would be up, B would be down, C would be down, and D would be up. All right. So that's like for a charge. Now we're going to look at a wire. So there's a loop of wire. So this kind of weird shape here with 1, 2, 3, and 4 labeled on it is a loop of wire connected to a battery. So this is a direct current battery, so several battery cells here. And it says it's placed in a magnetic field. The field is going, it looks like, to the right across our screen. And then we're supposed to determine a couple things here. So based on the setup of the battery, we're going to figure out the direction of the current. So I'm going to trace that out. So this side is the positive side, and this side is the negative side. So if you remember batteries, the long side is the positive side, and the short side is the negative side. So the current flows from the positive to the negative. So I am tracing it in the direction that it moves. So the current in each one of these sections of wire is going to follow this path. So that is kind of the direction of the current. So if I was describing this, I would say it's moving in the clockwise direction. So that's what I think for this setup. So I'd say it's clockwise. And again, it's because it goes from high to low. So then we're going to use the right-hand rule, but this time it's for a current in a wire. So it's the same essential rule. I is the direction of the motion of the current. So that's like the velocity in the other one. So that's your thumb. The fingers are the magnetic field, so that's going to be going to the right. And then your palm points in the direction of the force again. So it's the force on a wire this time. One other thing you should note, so for the magnetic force on a current carrying wire, it's ILB sine theta. And the sine theta part's important here because you have to look at the angle between the current and the magnetic field. L is the length of the wire that's in the field, so that's fine. So if you think about this, sometimes sine theta can go to 0. So that whole term goes to 0 when theta is equal to 0, or 0 degrees, or 180 degrees. So what that means is if the wire is running parallel or anti-parallel, so with or against the magnetic field lines, then this term goes to 0. Anything times 0 would make it go to 0. So if you look at 1 in section 1 of the wire, it's kind of the current's going that way. So that would be anti-parallel. And if you look at 3, it's going parallel. It's going the same direction as the magnetic field lines. So section 3 and section 1 are both, there is no magnetic force. So, but 2 and 4 do have them. So we're going to look at the forces. So I is going up towards the top of the page in 2. The field lines are going to the right. So if I hold my hand in that orientation, my palm is going to push in. So I would have like a force that has an X pushing in on that side of the loop. And if you do the other one, you got to tilt your hand so that your thumb points down and your fingers are pointing to the right, and your palm is going to push up. So you have a dot on this one. So, so those are the directions that correspond to what's going on here. And I drew that. So again, 1 and 3 are 0 and 180 degrees. So there's no magnetic force. And then 2 is going into the page, and 4 is coming out of the page. Because of that, this whole thing would rotate. So like this part would go into the page, and this part would come out of the page, and it would rotate. And you'd have this magnetic force turning this coil of wire. So that's number 3. Number 4 is basically using that equation again to solve for the magnetic force acting on a wire, but this time we're going to solve for the magnetic field. So it says a wire 1 meter long experiences a magnetic force of 0.5 newtons due to a perpendicular uniform magnetic field. If the wire carries 1 amp of current, what is the magnitude of the magnetic field? So we're looking for B is what we're looking for. So again, the length of the wire is L, the force is FB, I is the amount of current, and it says it's perpendicular, so theta is 90, which is makes sine of 90 go to 1. So if we plug into that equation and solve, I just kind of wrote that out. So FB equals ILB sine theta. You solve for B, you get 0.05 Tesla. So that is the strength of the magnetic field to create this amount of force with those conditions. The next one's another conceptual one. So this one combines a couple things. So this is the Lenz's law and Faraday's law, where you're inducing a field and inducing a current to oppose the changing flux. So in this one, it reads, a current in a long straight wire shown below is increasing uniformly. As a result, a current is induced in the neighboring loop. The current is what? So we're trying to figure out what's going on. So the current in the wire is going to the left. So we got to first figure out what kind of field a loop is going around that wire with current going through it. So if you grab the wire with your thumb pointing in the direction of the current, your fingers curl in the direction that the loop goes. So if my fingers are above the wire, they're going in to this, so that's why there's X's up there, and below there are dots. So if you're imagining down here, there are dots going through this loop of wire. So the dots mean the current, the magnetic field is pointing out. And what's happening to our current? The current is increasing uniformly. So what that means is it's increasing at a steady rate. So there are more and more lines coming through. So there's going to be a changing flux, which is going to produce a current. And remember, our current that's induced, the current that's going to go in this ring, is going to impose this change. So if there's more and more lines that are coming out as this current increases, the current from in the ring is going to oppose that. So you're going to have to put lines going in to kind of cancel them out and try to keep it at the same amount. So you're going to put your fingers so they go in the middle of the loop, and your thumb is going to point in the direction of the current. So the current is going to go around clockwise. And we have to decide how it's going. So it's not going to be counterclockwise, so it's not C or D, A or B. So so the current, if it's increasing uniformly, again, flux is equal to the change in, or I'm sorry, the rate of change of flux, delta flux over delta T. That's what causes the EMF, and then you would have the EMF divided by the resistance to get the current. So that's I. But the idea is it's the changing flux times A or BA cosine theta over T. And because this is changing at a uniform way, the current is going to be constant. So it's like it's continually getting bigger. So we're going to have to continually put these lines going in. So if like every second it adds a dot, every second we're going to have to add an X to cancel out that dot. And it's going to keep that current going in that manner. So the correct answer there is A. Okay. So this is just me talking through it, or that's the written version of me, what I just talked through. All right. So a couple more conceptual ones with flux. So it says determine the direction of any induced current as it enters and leaves the region containing the magnetic field. So we have this box of wire, or this loop of wire, and it's going to move to the right. And again, if you look at, okay, what's happening when it gets to the, so if this is the loop of wire, as it enters the field, or as it continually moves into the magnetic field, which is directed into the page, there are more X's. So the external field, there is an increase in X's, or directed inward, the magnetic field lines that are directed inward. So the induced current has to oppose that. So you're going to have dots. So we want dots. So those dots are going to come out. We're going to grab the loop of wire so that the induced current is going to make dots. So the induced current is going to go counterclockwise to start. So you're going to get dots here. So as we increase X's, we're going to increase dots as we move. And then when it's inside here, there is no changing flux because it's the same amount of lines because it's a uniform field. And then we have to examine as it leaves. So as it leaves, if we have that same area and it's moving to the right still, as it leaves, what's happening to the X's? The X's are decreasing, right? The magnetic field is getting less going through. So we want to oppose that change. So we're going to make X's. So we're going to put X's in here as it moves to try to keep the flux the same. So if you grab it so that you have X's, the current goes in the clockwise direction. So again, just kind of working through those concepts, I wrote it here. But as it moves through, as it enters, there's more lines going in. So the induced magnetic field has to go out, and to induce a magnetic field going out, you have to grab so that the current goes counterclockwise. And then exiting, there's less lines going in, so you're going to induce a field that goes in, and to get a field that's going in to put X's in the middle of the area, you're going to make the current go clockwise. So those are those two. A couple more. This one is an RLC circuit, so we worked on this last time. So it says an RLC circuit has a 40 ohm resistor. I should have a comma here, but I don't think I can fit it. 40 ohm resistor, a 3 millihenry inductor, a 5 microfarad capacitor, and it's connected to a 200 volt, 1000 hertz AC voltage source. We're going to find the capacitive reactance, so that's like XC. We're going to find the inductive resistance or reactance, which is XL. We're going to find the impedance, which is Z. We're going to find the max current, which is IO for maximum current. And then we're going to solve for the resonant frequency, which is where we have the circuit tuned to a frequency that would produce the most current based on having these two factors cancel out. So it's just the resistance, the resistor that's present when when it's tuned to the right frequency. So what I'm going to do is just kind of work through that. So the first one, oops, sorry. For the first one, so I just drew a picture. The first one, the capacitance, the capacitive reactance is 1 divided by 2 pi F times C. So F is 1,000. C is the capacitor, which is 5 microfarads. So 5 times 10 to the negative 6 is what I put there. It's 1 divided by that whole number. So if you do that, you get 31.85 for the number of ohms for that. So that's the first one. For the inductive reactance, it's a different formula. It's 2 pi F times L. So 2 pi times 1,000. L is 3 times 10 to the negative third because it's milli. So if you do that math, you get 18.84. So those are the two values for the reactances. Once you have those numbers, you can calculate Z. And the way to calculate Z is using this formula. So it's R squared, and I put in the wrong thing. It'd be plus, so that should be a plus sign. Let me make sure I did that right. So, but you put in these values, so it would be 18.84 minus 31.85. That answer squared, and then it would be plus the 40 squared. And then you take a square root of that number. So yeah, I did calculate it correctly. If I just made a minus sign there instead of a plus sign, my fault. So it's 1600 is 40 squared, and the 169.3 is what you get when you take the difference in those two and square them. So you take the square root of 1769.3 and you get 42.1 approximately. So that's the total resistance or impedance that the circuit has within it at that frequency. So to find the maximum current, it's basically Ohm's law, but it's for impedance, so it's Viz. So you're gonna do that. Let me just delete that thing because it's bugging me. So Ohm's law is V equals IR. For impedance, it's V equals IZ. So you're going to solve for I. So it's the voltage, which is 200, the max voltage is 200, divided by the impedance, which is that 42.1 number. If you do that, you get 4.75 amps. So that's the amount of current going through. And then finally, for the resonant frequency, that's again where basically this term just goes away, and that makes it have the least impedance possible. So it would just be 40 squared there for Z. And that happens when these two values equal each other. So when you solve this out, the frequency that occurs at is 1 divided by 2 pi square root of LC. So it'd be 1 divided by 2 pi times the square root of 3 times 10 to the negative third times 5 times 10 to the negative sixth. That should be a 6 there instead of a 5. I'm sorry. So let me double check my math there too. I think I did it right, but I just wrote it down wrong. So 3 times 10 to the negative third times 5 times 10 to the negative fifth. And then I'm going to take a square root of that and then multiply it by 6.28 and then take the inverse. So actually I did calculate this incorrectly. I apologize. Let me try to do that again to make sure it's okay. So it's 3e to the negative third times 5e to the negative sixth. The square root of that times 6.28 and then the inverse of that. Yeah, so this is not correct, sorry. I put in the wrong number here. So this should actually be 1300 hertz. So let me just check this to make sure it works. So if it's 1300 times 6.28 times 3e to the negative third, that's that value. And then I'm going to do the same thing here for the other one. So 1 divided by 6.28 times 1300 times 5e to the negative 6. Yes, so 1300 is the correct answer. I just verified it by making sure that these two things would basically get you the same number. At 1300, these values are 24.5 approximately. All right, guys, so the last one here is talking about a transformer. And it reads that a transformer has a primary coil with 200 turns, and the secondary coil has 2,000 turns. And it says the input voltage is 120 volts, and it runs at 1,800 watts of power. And you're going to try to fill out this table for the other ideas here. So, and then the answer, is it a step up or step down transformer? So, and explain how you know. So, you can answer this last question first if you wanted, or you could go through this and try to figure it out. But let's take this information and plug it in here, what we know. So 200 turns, that is the primary. So it starts out with 200 here, and it goes up to 2,000. So this idea is like N. This one is N1. And this 2,000, which I failed to write another 0, that's N2. So we have our two N values for the number of turns around the magnetic coil. And then it says this primary voltage is 120 volts, and it runs at a power of 1,800 watts. So that's that value. And we're going to try to solve for the currents in both the primary and secondary. We're going to solve for the secondary voltage and the secondary power. So if you look back in your notes, one thing that you should know is that the power is equal. So the power doesn't change. So this is 1800 watts again. So later on, that's going to be helpful. That's just kind of a rule for the transformer. It doesn't change the power output. It does change the voltage and the current though. So the equation that we're going to use is N1 over N2. Those are the number of turns equals voltage 1 over voltage 2. So that is the relationship between the volts and the number of turns in these primary and secondary coils. So if you plug into this, it would be 200 over 2000 equals 120 over V2. So we're looking for V2. If you look at this relationship, this is like 10 times, the denominator here is 10 times bigger than the numerator. So the same thing has to happen here. So if you do the math and cross multiply, you're going to get 1200 or 1200 volts for this voltage value. Once you have the voltage and the power, you can solve for the current because P equals IV. So with P equals IV, you just plug in, if we need to solve for this current, it's 1800 equals I, this would be I1, and the voltage of 1 would be 120. So if you divide that out, you get 15 amps here. And then you could do the same thing for the equation, but it would be I2, and you would change it from 120 into 1200. And that's going to change, you're increasing this voltage by a factor of 10, so when you divide it, shrinks this current by a factor of 10. So it'd be 1.5 amps for the output. So that's the whole chart, just kind of using P equals IV in this equation for the number of turns in comparison to the voltage. The last thing is it is a step up or step down. It is a step up transformer because you are stepping up the voltage. So transformers change the voltage, and the voltage is increasing, so that's a step up. If it was a step down transformer, you would be decreasing the voltage. So that's one way you can talk about it. Also, if it's a step up transformer, the number of turns increases, so it goes from 200 to 2000. If it was reversed and it started as 2000 and went to 200, that would be a step down transformer again. So you can look at the number of turns and decide if it's a step up or step down, or you can look at the voltage. Either way it works, okay? And this is just the answer. I just worked it out on the screen, but this is what's on your answer sheet there too. So I apologize for this one mistake, which that should be 1300. This number here is wrong. I will update that as well here for you. So it's all from that number here. So it should be 5 times 10 to the negative 6th. So 5e to the negative 6 times the 3e to the negative 3. And then the square root of that times 6.28, and then the inverse. So yeah, so that's right. So this number, when you do this, it's 1 over like 7.69 times 10 to the negative 4th is what I got. And then this number turns out to be really close to 1300. It's like 1300.15. So that's close enough. So that's the frequency that will cause it to behave at the ideal or maximum value of power output, because it is the least amount of resistance that it has here. So the current is the maximum. So that's the idea. So anyway, have a great one, guys. I will see you in class.